Okay. Next we have Matthew Millard from the University of Iowa, and he's talking about Chandra High Resolution X-ray Spectroscopy of Supernova 1996 CR and analysis of line profile.
No, I don't think that was me.
Oh, sorry.
I could try.
This is sorry, the title came before. Seeing between the lines, insights into supernova remnants with high resolution X-ray spectroscopy. How's that? You got that?
Sounds good. Yep,
Okay.
got it. All right, happy to kick off our talks here today. So I'll be giving a review of high resolution X-ray spectroscopy of supernova remnants. I'll start with the anatomy of a supernova remnant. So once the supernova goes off, you have this blast wave that's expanding into the interstellar medium at roughly on the order of 10,000 kilometers per second. And eventually, the interstellar medium starts to push back, and it produces a reverse shock, which travels towards the center, compressing and heating up the cool inner ejecta, causing it to emit in X-rays. So then you get plenty of thermal line emission. And so a great example of that is, of course, Cassiopeia A. It's a galactic core collapse supernova remnant. Pictured here in X-rays, each of different colors represents emission from different nucleosynthesis products like silicon, sulfur, calcium, iron, and the blue is synchrotron radiation. So in general, these nucleosynthesis products have prominent emission lines in the 0.5 to 10 keV band. So you see a lot of intermediate mass elements like silicon, sulfur, argon, calcium, iron group elements, mainly iron and nickel, also trace elements. And the presence of these lines indicates temperatures of around 0.2 to 5 keV. So this is a spectrum of Cas A, where you can see these hydrogen-like and helium-like emission lines from these products. And this is from a Chandra X-ray spectrum, so it's CCD. So we kind of consider this sort of a medium resolution spectrum. So what would a high resolution spectrum look like? I have two examples here, EO102 in the Small Magellanic Cloud and 0519-69 in Large Magellanic Cloud. On the right, you can see the medium resolution spectrum, the XMM MOS from the XMM MOS detector, compared with the XMM reflection grating spectrometer. So if you zoom into this region of the red box there, around 0.5 to 1.2 keV for EO102, well, you can see it's an oxygen-rich supernova remnant, so you can see very clearly that these lines become resolved. I think there are also some neon lines in there. For 0519, it's a type 1A. So when you zoom into that region, this just looks like some bump feature. It's not really clear what it is. But when you zoom in, you realize with RGS that it's actually kind of a forest of iron L lines. And so these observations with this high resolution spectrometer, the XMM reflection grating spectrometer, look very promising. Before I go on, I just want to mention that so the main high resolution X-ray spectrometers that we use currently are the Chandra low and high energy transmission gratings and the, like I mentioned, the XMM RGS. And so these tend to degrade with the spectral resolution tends to degrade with size. So there are ways. So of course, with the very extended source like a supernova remnant, that becomes an issue, right? So one way to deal with this is to just choose small features within the remnant. Right, so this is approximately the size of some features, some like an ejecta knot. So it's on the order of a few arc seconds. Or you could just choose smaller size supernova remnants on the order of tens of arc seconds. And of course, with the non-dispersive microcalorimeters like that was on the Hitomi with the soft X-ray spectrometer, this is not an issue. It has good resolution regardless of the size. Okay, so we have high resolution X-ray spectroscopy that grants us the ability to distinguish between closely spaced emission lines in an X-ray spectrum. So what insights can we gain with this ability? Well, one that I studied throughout my PhD career was kinematics. So if you take different lines of sight through a supernova remnant, like Tycho, then you can measure you can get precise Doppler shift measurements and thus get radial velocity, measure the radial velocity. So using that, you can reveal in detail a 3D structure, especially when you have errors that go down to on the order of hundreds of kilometers per second. And so you want to do this because you're interested in subtle asymmetries in the structure of the remnant that might tell you about the explosion mechanism, like how in the case of a type 1a supernova, how did the white dwarf explode? Or you can use it to investigate the properties of the surrounding medium, such as the density profile. So we're looking at something. We're looking for something that was sort of done in optical wavelengths with Cas A between X-rays. Right. So first case study, of course, is my own work. It's my last PhD paper. So this is the dispersed Chandra HETG spectrum. You can see the green emission is silicon K alpha lines. And so we chose several ejectonauts, about 60, throughout the remnant, and measured the Doppler shift using this bright silicon K alpha line. And so each of these are colored by shift. So green is no shift, blue is blue shift, and red would be red shift. And this gives you some idea of the morphology of each. They're roughly about 10 arc seconds across. So we were able to measure relatively high speeds of up to 5,500 kilometers per second, which were comparable to the proper motion measurements that we did, which suggests that in general, of course, Tycho is spherical. Well, that's kind of obvious. But when we looked in more detail, combining our radial velocity measurements with our proper motion measurements, we found that in general, the southeastern quadrant tends to expand faster than the rest of the remnant. And we may be able to attribute this to something to do with the explosion mechanism, since we don't see any interesting variations in the ambient density in that region. We also discovered this apparently large-scale asymmetry, where most of the knots in the northern half were blue shifted, and most knots in the south were red shifted. This one's a little more tricky to deal with, so this could just be due to differences in density between the front and the back of the remnant, which would create a stronger or weaker reverse shock at certain points, and so you would see just happen to see more knots in that region because of the stronger reverse shock. So not only can you measure ejecta using this method, you can also measure the velocities of the circumstellar medium. So this is an RGS study of Kepler. So Kepler is well known for having a significant amount of circumstellar medium surrounding it. This is in red, in blue, it's the CSM, red is the ejecta. And so in this study, they measured the Doppler shift of the ejecta, the CSM on the edge, and found that it's pretty much all blue shifted with velocities up to around 500 kilometers per second. So that means that the entire remnant is actually moving away from us with some certain speed. And this is roughly consistent with the theory that Kepler was a runaway AGB star before it exploded. They also measured the redshift and blue shift of the central structure here, and found that the northwest half was blue shifted, southeast half was red shifted, and so southeast half must be on the far side, northwest half on the near side, and so we have sort of a torus structure, which has been suggested for Kepler in the past. All right, so those were examples of kinematics. Well, we can also learn more about the plasma diagnostics. So we have several line ratios that you can use to estimate the electron temperature. And the better your resolution, the better you can measure those temperatures. You also have the ability to measure the ion temperature, which is a little bit trickier, since that's based on the width, the Doppler broadening of your emission line. And so a typical Doppler broadening corresponds to around 1 electron volt, which requires a detector with a factor of 100 resolving power. So really measuring these ion temperatures are only possible with these high resolution detectors. So one great example of this is in Supernova 1006, where they measured the where they took the spectrum of a bright ejecta in the northwest region of the remnant. So you can see the oxygen 7 line here, and you can see how it's sort of broadened in this close-up view. So they measured a Doppler broadening of around 2.5 eV, which corresponds to temperature of around 275 for the oxygen 7 species. And using CCD data, they measured the electron temperature at around 1.3 kV. So this gives a really good example how you can clearly show that these species are at different temperatures based on their mass. You can also measure the you can also study the evolution of a supernova remnant using these diagnostics. So for example, the evolution of supernova 1987A, it's been regularly monitored with Chandra since its launch in 1999. So this is the evolution of the X-ray image of Chandra, X-ray image of 1987A. And so it revealed a blast wave impacting the equatorial ring, which is this dense structure, this structure of dense circumstellar knots surrounding the remnant. And so it saw a sudden decrease in the blast wave velocity, dramatic increase in the soft X-ray flux at that time. And so it increased and increased, but at about 7,000 days, it starts to flatten out. This light curve you see here. And so it's possible that 87A is undergoing some sort of transformation, entering a new phase. Well, my PhD group member, Arvind Ravi, he studied the HETG spectra and LETG spectra of 87A over time. So he measured the ratios of the hydrogen and helium-like silicon and magnesium ions, and found that they are changing significantly with this new data, relatively new data in 2018. So this coincides with the changes in the electron temperatures, and also this emission measure here, also around the same time, is starting to decrease. And so they believe that 87A is entering a new transitionary phase where it's leaving the blast wave is leaving the equatorial ring, and now it's entering into a less dense wind from the red supergiant. In case you're wondering, they still haven't seen any change in elemental abundance, so the ejecta has not yet been shocked by any reverse shock. So we can also measure charge exchange and resonance scattering using high resolution X-ray spectroscopy. Just as a reminder, charge exchange is when you have one or more electrons that are transferred from one atom to another. The receiving ion or atom will have the electron left in an excited state. And so after the exchange, the electron will de-excite and it will release an X-ray. And resonance scattering is when you have a high column density along your line of sight, a high column density of ions along your line of sight. And so the resonance line from anything behind that is more likely to be scattered. And this has a significant effect on elemental abundances. So a great example of this is charge exchange, evidence for charge exchange in the Cygnus loop. So they got the RGS spectrum of not in the southwest region of Cygnus loop. They measured the forbidden to resonance line ratio of the oxygen 7 species and found that it was somewhat high. So they fit the spectrum with an NEI component, but added in the charge exchange component and found that that could very well, that very nicely explains the shape of the spectrum. And so after they add in this charge exchange component, then they measure the elemental abundance, and they find that still it's low compared to what you would expect. And so even with charge exchange included, we still have this issue in evolved SNRs, supernova remnants, this low abundance problem where you see abundances lower than you would expect. In N49, we have evidence of resonance scattering, again using RGS spectra. So it shows a high G ratio of the oxygen 7 helium alpha lines, and also other oxygen 7 and also iron line ratios, which can be explained through this resonance scattering. So they have the ISM component. This is the RGS spectra, so they have the ISM component in blue, the ejected component in green. And since resonance scattering means you're losing emission from the resonance line, they added in negative. Oh, okay. I'll have to talk to you after. Right, so they added in a negative Gaussian to those lines to account for that resonance scattering effect. And for the final case study, Hitomi observed N132D. It was this was just a couple of weeks before it was lost. So it was a very short exposure. Even during that time, it lost attitude. And so you can see here, this is the SXS field of view. So initially it started there, but once it lost attitude, then it started to drift away and it even fell out of the SXI field of view. However, even with this very short data set, they still found evidence of iron emission, which they found was highly redshifted at 800 kilometers per second. They didn't see a blue shifted component, so this could suggest that the iron ejecta is highly asymmetric there. So this is a great example of how the high resolution of the detector can overcome the low counting statistics. That brings us to CRISM. So CRISM, of course, is the recovery mission of Hitomi, which also used a similar detector in Suzaku. It's planned for August 26, 2023, as Pat mentioned. Has a fairly good spectral resolution, kind of mediocre angular resolution, but it's still exciting to use for supernova remnants. So we have a simulated Cas-A CRISM spectrum here. So that the spectrum is simulated from this clump region in black. And so the authors of this paper suggest that you can use the high resolution of CRISM to detect radiative recombination continua. Looking forward to after CRISM, in the 2030s, it's been proposed, the line emission mapper has been proposed. So it would have about 5 times the angular resolution and 7 times the spectral resolution as CRISM. So it'd be very, and also has a much wider field of view. So it'd be really an excellent instrument to observe supernova remnants with. Okay, I might be running low on time. So just want to say thank you to the committee for inviting me here, and CXC team for all the great work you do. You really make our lives easier. And if you want a more detailed review of high resolution X-ray spectroscopy of supernova remnants, please see this review by Satoru Ketsuda. Thank you.
Thank you. That's impressive work on objects for which the instrument wasn't designed.
Right.
But shouldn't let that stop you. Questions? Januva? I don't want to like miss and bonk somebody else in the head, but here you go.
Yeah, thanks for, can that be heard? Yeah, okay. Very inspiring talk. Thank you very much. Really interesting. A question and a comment about the resonance scattering. The first question, the plot with the sizes, as a, showing the resolving power. It's a bit surprised to see that the RGS performing so much better. Yes, and the right panel here can go so much further than the Chandra gratings. I wonder why that is.
Yeah, technically I don't know the details behind it.
Is it perhaps folding in the instrumental, the detector spectral resolution?
I think it might have to
increase the space, because you have the rough CCD spectrum.
Yes.
At the same time, so you can already filter out quite a lot of photons.
Oh, well, you can do that with Chandra too.
Exactly. Well, not with the LETGS, with the HETGS you can, but at 15 angstroms, the HETGS already has fairly low effective area. Maybe that's kind of in my mind. That's perhaps why the RGS is relatively well here.
Yeah.
Okay, don't worry, it's the technical details.
And it may have to do with the wider dispersion angle. I'm not sure about that. I have to check.
The mirror X-Men is not so good at Chandra, and therefore you can observe better extended source than Chandra. Chandra too good for this.
Yeah. Okay, I see. Yeah. Okay, great. Thank you. Yeah, thank you. Good point. And the comment just, sorry if I made, the optical scattering, I mean, whenever we're scattering, we scatter out of the line of sight, right? We also scatter into the line of sight. Most famous, the sky is blue. That's all photons. So all the sky, there's one spot, the sun, where you're missing the photons. So the sun is red at sunset, but then all the rest of the sky is blue where we're scattering into the line of sight. So the resonant line scattering is pretty tricky. I mean, you see the resonance lines being depleted, or they can also be enhanced depending on the geometry.
Yes.
Because if you have unfavorable geometry, that the light source comes from the right and the scattering goes into your line of sight, you see actually more photons in the resonance line.
Yes.
And keeping that in mind, if we don't see any effect, it could be balancing out. So we could have a lot more resonant line scattering in reality than we actually see when we do line ratio diagnostics of forbidden resonance lines. So it's a comment, so it's just easily forgotten, and but life is more complicated.
Yeah,
so
that makes
more common, really.
Even trickier.
Thanks.
Thank you.
Thank you. For those of you remote, you can put your questions into the Slack chat or the Zoom chat, and we'll pick them up for you. Other questions?
I had a question about Kepler. I thought it was interesting. I'm just not familiar. I thought it was interesting that something about a runaway AGB star. Can you elaborate on that a little bit? I mean, for example, is that common, or is there a fair number of AGBs that are runaways?
No, not that I'm aware of, but Kepler is well above the galactic plane. And so you can actually see in the northern part, this bow shock. So it looks like it's somehow exited the plane, and now it's moving through this medium there.
Okay, thanks.
Any other questions? Anonymous attendee asks, what was the reasoning you had given for different velocities in the Tycho slide? Great talk.
Reasoning for different velocities
in the Tycho slide.
Could you be more specific? Well, I'll maybe that
Let's go back
slide.
to the Tycho slide. And,
Different velocities. Maybe the asymmetry.
yeah, perhaps for the different systematic velocities in the red and the blue.
Oh, well, I mean, that's just based on the Doppler shift, so. Yeah, yeah, just,
I think it's possibly asking if you have any explanation for the asymmetry.
oh,
Or the-
okay, yeah, no, I don't. That's very hard to speculate on, especially since, like I said, it could be due, we're just seeing more. It could be due to the fact that we're just seeing more of those on a certain quadrant because there's more dense material there, which would cause a stronger reverse shock and which would basically light up more of the ejector there, so you would see it. And it's, on the other hand, it actually could be due to some particular way that the progenitor of Tycho exploded. It's a type 1A supernova. So
Okay, thank you. Any last questions? Or just
So in one of the slides, you mentioned the temperature is like the temperature of oxygen 7 is somewhere around 275 keV.
Mhm.
So is that a real temperature or like you're just inferring that from the broadening?
yeah, that's the ion temperature. So yeah, you get the you can estimate the ion temperature from the width, the broadening of the line. So the
Yeah,
thermal
but that's oxygen 7 and 275 keV is like a really high temperature. So I wasn't sure like, and just in the next line, you mentioned a different temperature. So are both of these real temperatures? It wasn't clear which temperature. Yeah, so
one is the electron temperature and one is the
yeah.
ion temperature. So
So does that just mean they're not in like equilibrium or?
yeah, that's exactly it.
Okay, so yeah, I just wanted to be sure what exactly.
okay. Ioanna, you had one more question? Yeah. Okay, last question before we move on.
Yeah, thank you. Really inspiring talk. So you talked about abundance measurements that were lower than expected. Are these absolute abundances? So relative to hydrogen? Because we don't have hydrogen lines in the spectra. So I mean,
Oh,
if
sorry,
you
too far.
find the ions you find here with what you say low abundance, could also be more hydrogen around that produces more electrons if you determine the absolute abundances from the Bremsstrahlung continuum.
Yes, that's a great question. I'll have to get back to you on that.
Okay, good. Okay, thank you.
Okay, thanks again.
Thank you.
And now we switch to a remote speaker, Vikram Dwarkadas from University of Chicago, speaking about the Chandra High Resolution X-ray Spectroscopy of Supernova 1996 CR and analysis of the line profiles. Vikram?
Hi, thank you. Can you hear me? Hello, can you hear me? I can't turn on my video and can you hear me?
Yes.
I can't seem to turn on my video. It says it's okay.
As long as you can share your talk, or as long as we can share your talk. Well.
Just upgrading with photos.
Okay. Okay.
For some reason, I don't know, it won't let me turn on my video as I'm saying. It says it's prohibited by this. So can you turn on my video, please?
We're looking at it.
It's on, but it says it's prohibited by the host.
I'll work on that. You can talk.
Okay, should I go on anyway?
Yeah, go ahead.
Okay, great. So today I'm going to be speaking on Chandra High Resolution X-ray Spectroscopy of Supernova 1996 CR and analyzing the line profiles. This was work that I started with Franz Bauer and Dan Dewey many years ago, and lately we've continued with Franz Bauer and his graduate student, Jonathan Curola Vasquez. So I guess the first question you might ask is why 1990 CR? What's so special about it? Well, here you can see the light curves of most supernovae, not all, but most X-ray supernovae are shown here. Now, every X-ray supernovae except for one is a core collapse supernovae because that's what we see in X-rays. There's one type 1A CSM. Core collapse supernovae evolve in the winds of their massive stars. And so, the wind density is supposed to decrease with radius. So if it's a steady wind, for example, the density will decrease as 1 over r squared. The supernova are evolving inside this wind then will also decrease in luminosity because the luminosity is proportional to the density, essentially. I mean, there's more that goes into it, but that's the basic idea. So as you can see, most supernova light curves, the luminosity will decrease with time. But there are a few exceptions. So exception number one that we saw many, many years ago was supernova 1987A. And this is pretty well known that its X-ray emission was increasing with time from about like 3 years or so, if I remember. And the reason for this increase is basically that the supernova forward shock was hitting a very high density region in the equatorial plane. Now, at the beginning of this century, my colleague Franz Bauer found another supernova right here, supernova 1996 CR. And that seemed to be evolving in a similar fashion, that its density was increasing. I mean, its luminosity was increasing with time. And so this was quite surprising. It was only the second supernova after 87A where we had seen this. And, he wrote a couple of papers and we wrote a paper saying that it's supernova 87A's second cousin. In fact, just to jump ahead a little bit, I'll show you the full light curve, which is today's. And you can see that the luminosity increased quite a bit up to a certain maximum and then decreased again. This is, of course, a more recent light curve. But at that point, we could only see up to this increase. So once we saw it increasing, we knew that there was something different about this supernova and we wanted to investigate it further. So in order to investigate it further, we decided to we put in a proposal for a Chandra high energy transmission grading 500 kiloseconds. And the proposal was accepted and the data were delivered. And we got this beautiful spectrum that you can see down here in the lower panel. It's a 480 kilosecond Chandra HETG spectrum. The amount of lines that you can see and the resolution of the lines is pretty spectacular. So now that we had this, we decided that, of course, we had to learn a bit more about the supernova. The first thing we wanted to do was to actually see if, what can we learn about the evolution of the supernova? So we decided to do hydrodynamic simulations, calculate this spectra and light curves compared to the observations and see how they compare. So somehow this is giving me a lot of problems. So we carried out hydrodynamic simulations. I don't have the time to actually go into details, but you can look at this paper that we published in 2010. But just to give you an idea of the hydrodynamic simulations, basically from supernova 1987A, we had learned that it's interacting with a high density medium. So we tried the same thing out here. So here you can see in black the supernova ejecta profile. In blue, you can see the surrounding medium profile. So initially the surrounding mediums was very low density, and then you have this high density shell around it. So the supernova goes in this low density region that interacts with the high density shell, and the emission begins to increase. And you will see that in this animation right here. So if you can see this animation, the white is the density and the blue is the pressure. In the lower plot, you're going to see two curves. So the top curve will be the 2 to 8 keV X-ray luminosity. The bottom curve will be the 0.5 to 2 keV X-ray luminosity. So if we let it run, and I stop it here, you can see there's a forward shock and a reverse shock and a contact discontinuity, as you would expect. At the moment, you see no X-rays just because they are a very low level. But if we let it go on, and the moment the supernova shock hits the high density region, you can see that the X-ray emission begins to rise. This X-ray emission will continue to rise as the supernova expands into the high density region. So you can see that it continues to rise. Eventually, it'll sort of become stabilized. And you can see that the supernova shock is now at the edge of the high density region. As it comes out from the high density region, the emission begins to drop, but then you can see that the reflected shock from this interaction is now interacting with high density. And as the reflected shock interacts with high density, the emission will sort of rise again. And then eventually all the emission will decrease with time because the forward shock is decreasing and the reflected shock emission is decreasing. So this is the kind of light curve that you expect. It corresponds very well to the observations, as you can see, at both the hard X-rays and the soft X-ray level. So it matches very well with the observations. We also calculated the spectra. As I mentioned, I won't go into details. It's pretty complicated with non-equilibrium ionization calculations, but you can read the paper. But basically, if I play the spectra out here, we calculated spectra at every time step. What you can see out here is that you get like, basically the red is the total spectrum. The total spectrum consists of the spectrum from the forward shock, which is the blue, and the spectrum from the reflected or reverse shock, which is the black. Now, initially, the spectrum from the forward shock basically contributes to almost all of the emission. So the forward shock is dominating, as I told you before, in the high density shell. The reflected or the reverse shock doesn't contribute much. But as time goes on, the forward shock emission decreases, the reflected shock emission increases, and around 8 years or so, the reflected shock emission begins to dominate. And eventually, it's the reflected shock emission that dominates the air. So the spectra also compare well with the light curves. As you can see, with the other observed spectra, here are the spectra in 2000, 2001, 2004, and 2009. And you can see that they all compare pretty well. So the spectra compared pretty well, of course. What we also realized, though, was that we had this beautiful spectra, and we had really high counts in individual lines. We had more counts in some individual lines than you actually have in supernova spectra in total. So we had a few hundred counts in some of the individual lines like silicon and sulfur and iron. So we decided to investigate the lines in more detail. And here you can see the hydrogen-like silicon line in blue and the hydrogen-like iron line in red. Okay, and you can clearly see that the line shapes are quite different. Okay, so what makes the line shape so different? That's something that we wanted to see again. What makes the line shape so very different? That means that they are basically having different physical or geometrical origins. Okay, so in order to investigate this, why would you have different physical or geometrical origins? Why would you have different line shapes? Well, you may have that the line of sight from us to the supernova is different. You may have that basically the flow is not completely spherical, but it's somewhat collimated. It could be that, emissions coming from the backside of the supernova, but that emission could be absorbed by some of the ejecta, so the emission from the backside is less than the front side. All of this could contribute to different line shapes. So in order to study this, what we did was that we wrote a model called a shell blur. It's an expect convolution model. And we used the shell blur model and expect to study the spectra and study the line shapes. And as I said, we keep saying we, but most of this work was actually done by Franz's master's student, Jonathan. And so he did most of this work, I should mention. Okay, so we wrote this shell blur model. We put it into expect. And by the way, it's available for anyone to use an expect for your own spectra. It'll come in really useful for CRISM spectra also. And so we applied it to our 2009 spectrum. And you can see that, of course, we matched the spectrum pretty well, but now we also match the line shapes, the line profiles pretty well. So here you can see silicon, sulfur, argon, and iron. And all of the line profiles are matched pretty well. And in order to match this, we required two components. So both, they had different temperatures, different geometries, and different absorptions. And I'll show you that in a minute. So we required a two-component spectrum, but they matched the 2009 spectra as well as the line shapes very well. And again, you can read details in our paper, so it's pretty complicated. We also applied it, of course, to the other spectra. So here you can see it applied to the 2000 HETG spectrum. Again, it matches the spectrum pretty well as the line shapes. Of course, this spectrum is not as well resolved. I'd like to point out one thing that we can't understand. Next to iron, we see this excess emission between 7.2 and 7.5 keV. I hope you can see that. There's like about 11 or 12 counts in there above the continuum. So it's definitely some excess emission. We don't know what lines these are. So if somebody has some idea, please, we would like to know. Okay, so going back to the two components, what we have is that I said that we had two components. We just call them the red component and the blue component, for want of anything better. As you can see out here, the various properties. So first of all, the temperature. The red component has a much higher temperature than the blue component, almost by an order of magnitude. Okay, next you can look at the half opening angle. So the half opening angle is basically 90 minus theta min. And what we find is that the half opening angle for the red component is around 20 degrees, the half opening angle for the blue component is therefore around 60 degrees. So basically the red component is much more collimated than the blue component. Okay. If we look at the absorption by the ejecta, we find that the red component is much more absorbed by the ejecta than the blue component. And therefore, we think that the red component might be behind sort of the blue component. I'll come to that in a minute. And finally, if we look at the ion abundance, we find that the red component over time is basically going into a region which has more and more supersolar ion abundance. So the red component, the ion abundance, is becoming more and more supersolar. So if you combine all these properties, especially the ion abundance and the fact that it's being absorbed by the ejecta, we can easily associate the red component with the reflected shock flow that I showed you before, which is expanding deeper into the ejecta. And as it goes deeper and deeper into the ejecta, it basically encounters more and more supersolar ion. Okay, so that makes sense. And then we associate the blue component with the transmitted shock expanding out from the dense shell. So the red component with the reflected shock that we talked about before, the blue component transmitted shock. The big difference, of course, is that the red component is more collimated, 20-degree half opening angle. The blue component is somewhat collimated, but not completely. It's a 60-degree half opening angle. So how do we explain all this? Well, we say that there's some asymmetry. And there has to be some asymmetry in either the surrounding medium. So for example, the surrounding medium can be oblate. The surrounding medium can be more concentrated at the poles than at the equator. Or also, which is my favorite, is that basically there's an asymmetry in the ejecta as well as the surrounding medium. So the ejecta basically have a jet-like appearance and the surrounding medium is more concentrated at the poles or something like that. But there has to be some asymmetry. And I think that more likely it's in both the ejecta and the surrounding medium. The point of this whole thing is that no matter what kind of asymmetry there is, basically the reflected shock that comes back from interacting with this high density region must be like collimated into a narrow half opening angle, in this case, which is 20 degrees. So as you can see here in this picture, this reflected shock coming back is not spherical, but must be sort of collimated. So basically, just by looking at the line profiles, we can actually get a picture of the 3D morphology. And with that, I'll put up my conclusions because I think I've exceeded my time. I just wanted to mention that for once we can accomplish what supernova optical astronomers are doing regularly. So we can explore geometrical models to describe the line profile. We can actually look at the 3D morphology of a point source extragalactic object, which is rarely done in X-rays. Okay, but we can do this with this, and we can monitor the line evolution. And of course, when more telescopes like CRISM goes up, we are going to be doing this much more. We are going to get many more supernova like this. So this is kind of a harbinger of what we are going to see more. And this gives us a template of how we interpret this emission. And with that, I'll take your questions and I'll stop here. Thank you very much for listening. Thanks.
Thank you. Any questions? Yes. Talk to the box.
Hi, could you elaborate a little bit more on why you think the anisotropy or the geometry of the system will explain the superabundance in iron? I don't quite get that part.
Oh, the geometry won't explain the superabundance in iron. The high ion abundance we are saying is basically because you just have high ion in the ejecta. And this reflected shock, which is highly collimated, is sort of going more and more. I mean, it's going deeper into the ejecta. If you remember, the simulation I showed you, obviously the reflected shock goes back into the ejecta. And as it goes back, it's encountering more and more ion-rich layers. And that's what explains the superabundance in iron. So,
and that abundance is something that you would expect in this kind of supernova?
It's possible. And I guess the one thing is that the geometry does contribute somewhat, because the geometry, it's so collimated that, it's there's less fluid encountering more iron, and so you get this. But yeah, it is something that we would expect, that it's a very iron-rich supernova. I mean, it's a very iron-rich ejecta, and that's not uncommon.
Well, there's a question from online. It's Junji Mao. What causes the soft X-ray excess when comparing the simulated and observed spectrum?
Oh, I think that, let me see. Are you referring to the fact that we have this emission which we don't match below 1 kV or something? I think that's what you're referring to. And actually, I'm not quite sure about this. We asked a few people about it, actually. One of the things that we were told is that, there is a lot of INL emission in that region, and we probably didn't have it in our databases. So we just used, the way we did this, we basically used this thing called ISIS, and we used whatever was in the database there. And I think at that point it was using expect2, and a lot of the INL lines were not there. So we think that that's something that we are missing, that a lot of this emission at low energies is basically not being caught. Surprisingly, in the 2001 XMM, we are matching it quite well, but in all the Chandra spectra, we are not matching it. That's something that I still don't think we understand very well. It could be the INL lines. If somebody else has a better explanation, we are very willing to listen. It matches everything above 1 kV much better.
Okay, one more quick question, quick answer.
I was wondering whether, based on these observations, you have already inferred something about the progenitor.
Oh, yes. So we did. It was in the 2010 paper. I didn't go into it in detail. We basically inferred that the progenitor was essentially a Wolf-Rayet star, and I think I have it somewhere here. Yeah, so we basically inferred, we looked at basically we said that it was interaction of a fast wind with a slow wind. We tried to calculate the wind parameters that would give us this kind of a structure, a hydrodynamic structure, and you can read the paper, the 2000 paper in detail. And from the wind parameters, we inferred that it was more or less more like a Wolf-Rayet progenitor. We couldn't exclude an 87A type of blue supergiant progenitor, but when we looked at the abundances in detail, and again, you can look at the paper, they match much better with a Wolf-Rayet star. So we were very confident that it was a Wolf-Rayet progenitor.
Okay, thank you.
Thanks.
Thank you again.
Thank you very much.
Okay, next we have a remote flash talk, a 3-minute talk. An evolutionary optimization approach towards unraveling high-resolution X-ray imaging and spectroscopic studies of supernova remnants, Austin MacMaster, University of Manitoba.
All right, hello, thank you. Can you hear me okay? Oh, hello, can you hear me?
Yes.
Okay, perfect. Great, thanks. So, supernovae and their remnants are part of a complex cycle of stellar formation through cloud collapse and transformation following one of multiple mass-dependent progenitor explosion scenarios, leading to the formation of some combination of compact object, shell of shocked and heated material, and wind nebula. This leads us to ask if there exists a diagnostic relationship between the properties we observe in these remnants and their progenitor explosion mechanism. Through the selection and minimization of an objective or fitness function, astrophysical models can be fit to data collected by telescopes such as Chandra in order to inform how well these models predict observation. So things like correlated parameters in nonlinear models, systematic uncertainty and noise, as well as spectroscopic line components, all increase the likelihood of degeneracy occurring within the parameter space of objective function solutions, where two or more different sets of parameter values may evaluate to the same or similar fitness function values. Now, conventional optimization algorithms use a gradient-based single-agent approach to minimizing the fitness function, which has a tendency to get stuck in local minima and is only capable of outputting a single objective function solution, potentially missing out on other better or degenerate solutions present in the broader parameter space. Evolutionary algorithms, on the other hand, are based on the principles of natural selection. Their gradient-free multi-agent approach seeks to find satisfactory results as opposed to a purely optimal solution, meaning that they have less dependency on the initial values of the search and are capable of outputting families of degenerate solutions. G41.1-.3 is a supernova remnant characterized by a heavily absorbed thermal spectrum with many emission lines. In 2014, Yamaguchi et al. Found a possible diagnostic relationship between the luminosity and centroid energy of the iron K alpha emission line, separating type 1a and core collapse progenitor scenarios. In 2021, Siegel et al. Demonstrated a spatial dependence in the iron K alpha emission of G41, with centroids falling on either side of this type 1a divider line, depending on the extraction region used. My interest is in using archival and future high-resolution spectroscopic data in order to study the fine structure contributions to these line strengths and study and explore the possible degeneracies in these line populating ions, with hopes of better constraining these centroids. Recently, we used XFIT, an evolutionary optimization algorithm, to fit a 29-parameter absorbed 2-component thermal model with 8 emission lines to the Chandra spectrum of the western lobe of G41. We find this fit with random initial parameter values for the search, which demonstrates the power of these gradient-free methods. Currently, we are working on implementations of outputting degenerate solutions for this object in preparation for CRISM, scheduled for launch later this month. So keep an eye out for this, and thank you. That concludes my talk, and I look forward to answering any questions you might have in the chat.
Am I unmuted? Okay, thank you. And for all the flash talks, just as a reminder, we will skip the live Q&A and use the chat, use the Slack for Q&A for the flash. Okay, last talk of this session, Mineralogy of Interstellar Dust in the X-ray Regime, Ioanna Psaradaki from the University of Michigan. Oh yeah, she needs that.
Okay. All right. Okay. So hi everyone, it's really great to be here. In this talk, I will speak about interstellar dust. So we shift towards the diffuse interstellar medium. I won't talk about supernova remnants, but I promise, I hope I can give you some nice overview of how we study the dust grain chemistry using high resolution X-ray spectroscopy. But first of all, let's set the stage. So interstellar dust is ubiquitous in the galaxy. It's very important for many astrophysical processes, for example, in star formation. And it's mainly characterized by 3 things. There are 3 properties that we study in this field. The first is the chemical composition, basically the elements that make up the dust grain. The second is the lattice structures, or what we call crystallinity. And this is basically the way that atoms are organized inside the dust grain. So we have the crystalline grains where the atoms are. We have an order, are in an order, and the amorphous where basically the lattice structure is disordered. And the last property of dust grains that we're interested into is the size distribution. So dust comes in different sizes in the interstellar medium. And here in this talk, we approximated with a parallel, or what we call as the MRN size distribution, with these sizes. So now, the big question in this field of astromineralogy is, what is interstellar dust made of? So we know today that in vast majority is composed by carbonaceous material, mainly the form of graphites or silicates. And silicates is a very important group of minerals that are made mainly by magnesium, silicon, oxygen, and iron, which are also the elements that you find in abundance in the crust of our planet, mainly silicon and oxygen. And there are 2 famous groups today, the olivines and pyroxenes, as we call. And the main difference here, please note, is how many oxygen atoms those compounds have. So for olivines, we have 4, and for pyroxenes, 3. And it's important to understand this because we can understand how much oxygen is locked up in the dust grains. We know that oxygen is only mildly depleted into the ISM, but still is very abundant. So we have a lot of it into dust. So it's important to take it into account when we study the oxygen KH, for example. Other than silicates, we also have dust in oxides, sulfates, and also some metallic iron. And an open question in the field has to do with the amount of iron that is locked into the dust grains and how actually iron gets condensed into the ISM. So we don't know yet if interstellar silicates are iron rich or iron poor, and how does this change in different density environments of the ISM, for example, and what is the ratio of magnesium to iron in silicates. So high resolution X-ray spectroscopy is really a great way to answer these questions, because first of all, we have the photoabsorption edge of all these elements that are into dust, into the X-ray band. And also we can study in detail the dust grain chemistry through the X-ray absorption fine structures. I'm sure most of you know this cartoon, which it shows briefly what's the process behind it. So when we have, let's say, the simple case of an atom, we have an X-ray photo interacts with it, and the eject photoelectron will create our edge at the binding energy of that removed electron. But when we have the dust, we have multiple atoms, and the ejected photoelectron will interact with the neighboring atoms. So we're going to get around the edge these structures, these wiggles that are called the X-ray absorption fine structures, and they're characteristic to the dust grain chemistry. If we model those, we can understand the dust grain properties in the ISM. And this is an example of models. These are models in the silicon K edge. So here in the last panel, we have two different types of dust chemistry. And we can see the difference in the XAFS pattern here, for example. In the middle panel, we see the same dust grain chemistry, but different crystallinity. We have crystalline versus amorphous dust. So as we see here in the orange line, when the lattice structure gets disordered, then the profile gets mirrored out, the absorption cross-section profile gets mirrored out. And here in the first panel, we have extinction cross-section compared to the previous that I showed, the absorption cross-section, where two different size distribution, the size distribution have been taken into account. So in the blue one, we have larger grains, and the scattering component of extinction becomes larger. So this is a way to understand what size of grains we have. So that's all great, but in order to actually study the dust grain properties in the ISM, we need dust extinction models to fit our high resolution X-ray spectra from Chandra and XMM. So there was a laboratory campaign that happened the previous years at Esron in the Netherlands. So it's a big group effort, and we acquired measurements of interstellar dust for about 20 dust samples of different chemical compositions. Some of them were natural from meteorites, some other were synthesized, and there were most of them were in both crystalline and amorphous atomic configurations, so we can study also the crystallinity of interstellar dust. And we took measurements for all the silicon, iron, magnesium, and oxygen K edges, so that we can have all our dust models to fit the data with. I'm going to focus on the iron and oxygen here, and basically the iron L edges and the oxygen K edge. So once we had our dust models, our laboratory measurements, actually the oxygen K and iron L edges, we computed the dust extinction cross sections. I don't have time to go into detail to the calculations. But we basically had this about 20 models, and we wanted to actually fit data of low mass X-ray binaries. So we choose low mass X-ray binaries because we can basically, we don't have complicated emission lines, for example, that could hamper the identification of XAFS features. And in order to study the oxygen and iron L edges, we needed sources with column density about 2 to 7, 10 to 21 to have enough optical depth there. And of course, availability of data in the Chandra and XMM archives, because we combine these two telescopes, and bright sources to have enough signal. So this is the bunch of sources that the sample that we came up with. And I'm going to present the results from this first part. So this is an example spectrum. This is Chandra HETG in the iron L edge, and this is XMM Newton RGS in the oxygen K edges. So what we basically do, what is the recipe? We want to fit simultaneously those edges. The more you fit simultaneously, the best, because you can constrain a better continuum, and you can also have the abundances free, so you can get a better understanding on how are these elements locked into dust. So we put first the gas phase models. We use SPECS X-ray fitting packets. So we use a model that takes into account the ionization balance. And then on top, we put the dust. So what we do is that we fit with all possible combinations of dust. So if we account like 20 models and all the possible dust combinations, we have more than 1,000 models to choose from. And after performing statistical tests, we can understand what is the dust grain chemistry in the line of sight we are choosing. So here you see, for example, in the iron edges, here's the transmission of dust, and we see that it takes most of the absorption. So iron is highly depleted into dust, we expected. But the situation is a little bit different in the oxygen K edge, because we have a lot of contribution from the gas phase models. There's a lot of neutral oxygen, for example, in the ISM, but there's also contribution from dust here. So it's important to take it into account into the modeling. So these are our results from this first sample. So we found that the dust grain chemistry in the diffuse interstellar medium, what we probe through the oxygen K and iron L edges, is mainly characterized by magnesium-rich amorphous pyroxene with this stoichiometry and some metallic iron. We find an upper limit on dust crystallinity of 15%. So infrared studies have showed about 2% of an upper limit of dust crystallinity, which, if we speak strictly, we are consistent because these are upper limits. But if there is any discrepancy, then this could be attributed to the nature of the X-rays, because we are actually probing, we may be penetrating the grain, and we may probe some short range order of atoms, so we may see crystallinity in partially glassy materials. And about abundances, we find that about 10 to 20% of oxygen is in dust, and more than 90% of iron is in dust, which is not surprising. So what we found is some slight underabundance of iron with respect to solar abundances. So what's next? We actually want to explore first more sightlines, and second, we want to calculate our models assuming larger grain sizes or different sizes should be used. So maybe we can find our missing iron there that is locked into larger grains. In the last minute or two, I would like to speak a little bit about CRISP. I guess we're all looking forward to CRISP this month. And among other research topics, will be great also to study the dust grain chemistry. There are many PV targets that are suitable to study the ISM absorption. And here I show a simulation into the silicon K edge of GX13+1. The data have been simulated using archival Chandra HETG data. So basically in the model, we assume both the dust. So here you can see the transmission of dust in the silicon K edge, and also highly ionized gas. This source shows absorption lines from some highly ionized species of silicon. So CRISP will be great not only to disentangle these two phases of ISM, or some of it comes from the source, I guess, but also to study the different dust size distribution. Here you see in red and blue, we see small grain sizes. And here in green, we see a model with larger grains. So basically, we'll see how greatly we can distinguish between these two with CRISP. So we're really, really looking forward to, so fingers crossed. And I'll leave you with my summary.
You question?
Very nice presentation. Enjoyed it a lot. You brought my horizons a lot, which certainly is not a challenge. Okay, so there are a number of sources also which are actually 10 to 100 times brighter than the ones you select, the super soft sources, which at least for the oxygen edge are, and they show quite a lot of details. I would really like to get in touch with you on that. So, but of course, the question would be also for the sources you have selected. In order to model these little things, you need to make some assumption about the continuum. And then you also need to know the local emission. How do you disentangle the fine structure in the local emission from the fine structure in the dust?
Yeah, so luckily most of the sources, they're very well studied in the literature. So we can cheat a little bit there and see, start from somewhere, right? Yeah, so we actually apply also models to fit the whole continuum. So when we feed the RGS data, we try to fill the whole band. Sometimes it's challenging because the continuum really affects how you study the X-ray absorption structures. But when we feed the dust, we actually have, when we feed it with different compounds, we actually have also the continuum parameters free. So this can compete among them. So we can, one problem that we kind of found the solution, especially when we feed both oxygen and iron, is that you can have some degeneracy between the hydrogen column density and the abundances. And also the continuum affects also for that in the modeling. So luckily, we have some idea what's the hydrogen column density in some sightlines from Calberla studies, for example. So we always have to keep in mind keeping our values in it. Yeah, but yeah.
Thank you. Wonderful talk. Enjoyed a lot.
Any other questions for Ioanna? Okay, Javier? Yeah, how far back?
So maybe you said it and I didn't quite get it, but the 10 to 20% oxygen that you found should be in some compounds, does that agree with the amount of oxygen that you would expect to be locked in the amorphous silicates with iron? So putting the two things together is what I'm thinking about, is that you find about 90% of iron needs to be in some kind of compound. There's lots of metallic iron, but there's lots of pyroxenes and all this stuff that you find. They all have oxygen on it as well. Do you try to compare the two numbers at all?
Yeah, so this 10 to 20% comes from the stoichiometry, right? So if you basically we have this compound that is the dominant, and you account how much oxygen atoms you have and how much you're missing from the gas phase, and then dust fills this part. Actually, we get a slight overabundance of oxygen, but we're near the galactic center, so I mean the galactic plane actually. So that might not be that bad. About metallic iron, because yes, I think it's but we didn't find much, like about 10 to 20%. That's how much this doesn't have oxygen, of course, but yeah, it's yeah.
Okay. What? Did you have a question?
A quick one.
Okay, quick one. Last question. Then it's copy break.
In the simulation of Christian simulation of GX 13+1, I don't know if you also simulate the GX 340. How the sulfur edge look like? Can we do this study? Can you do this study with dust models? It's the optical depth is good enough.
I haven't simulated sulfur, but I think it's in the program to do also. Yes, I cannot tell you details, but maybe we can look into that. Yeah.
Okay, thanks again, and thank all our speakers of this session.